Now, look at this. Doesn't this look a lot like what happens with the multiplicative function business? Based on that theorem I just described. Let's just add the d component on outside of this. D of 18 equals d of 2 times d of 3 squared. Now, look at this. We have something nice and simple to attack. What's d of 2? 2 is a prime number. If you recall, any prime number under d function is 2 times. So now look at this case. This is our p to the s issue right here. And we've already figured out that that has s plus 1 factors. And right here it's 2. So we go 2 plus 1. So we have 3, 2, 6. So we have 6 factors. And this gives us our number of factors every single time, given for a positive integer greater than 1. Let's do one more example with the d function. Let's do something that breaks into a bunch more pieces. Say, let's try 5 times 2. Let's definitely do something a little bit more fun. How about... Okay, let's just create one that's fun. Okay, let's just adapt our one we had before, 18. And let's add say, based on the unique factorization theorem, I can quickly do this really quickly. Okay, so we go 2 times 3 squared. Let's multiply it by 5. So we don't need to care exactly what value this is, really. So now we got ourselves something with 3 factors. And let's add 7 squared onto each side. So multiplying by 5 times 7, let's do 7 cubed, sorry. Now, d of 18 times 5 times 7 squared is d of 2 times d of 3 squared times 7 cubed. Sorry, there. Oops. 5. And now this guy right here is d of 2. Notice I'm breaking now this guy up into pieces. Times d of 3 squared times d of 5 times 7 cubed equals d of 2 times d of 3 squared times d of 5 times d of 7 cubed. Now we have ourselves everything in its base case, say in our algorithm here. We're basically dissecting the d function based on this multiplicative factor here. This theorem is very vital to this d function behavior. Okay, so d of 2, that's just 2. 3 squared. This is just 2 plus 1 because it's s is 2, so we go s plus 1, 2 plus 1, times 2, because this is a prime number, times 7 cubed, which is, let s equal 3, so it's 3 plus 1. 2 times 3 is 6. 2 times 4 is 8. 48 factors for this guy over here. And the answer is 48. That should cover basically what a d function is. Just for a recap. Prime numbers are not positive integers, or you can treat them as negatives also, but just for our sake in number theory, we would rather just refer to them as positive integers, where there only exists 2 factors. The prime number p and 1. Only 2. Factors. A factor is essentially an integer that can divide that positive integer n. So say k. For example, when we have 4, 2 divides 4. Because so 2 is a factor, sorry. 4 is also with 4. But let's say 2 is. Then we talked about unique factorization theorem, where basically you can write out a unique sequence of products. And now, with counting factors, which is important, note that this has very, very tedious issues in computational number theory, but you can apply that multiplicative concept to eliminate the complexity of using a lot of logarithmic computations of different bases. Counting factors can get really nasty when we start dealing with big numbers. That's when other tools, say like modulo arithmetic, will come very handy. But in the sake of factorization, the function will help you out with counting factors, because that essentially returns the value of your number of factors. And based on two conditions, that d of p equals 2 and d of p to the s equals s plus 1. And because you can always develop these into these base cases by the unique factorization theorem, you can use these two conditions to compute your algorithm to count the number of factors. You can do this by hand. It's actually very cool. I highly suggest trying this out. It's actually pretty cool. It is much cleverer than it actually looks. On this note, I'd like to conclude, say thank you. Have yourself a beautiful day.